Okay, let's say we have a slab of material. And let's say on this side, we have a neutron that is traveling in that direction. In very simplistic terms, what are the possibilities that can happen to this neutron as it interacts with that slab of material?
You could just collapse into it and, I don't know, just stay there.
Well, collapse isn't really a term we use for nuclear, but what could happen when it hits the slab?
It can be absorbed by the material.
Okay, it could be, we could have absorption.
We could have elastic scattering.
Okay, and rather than just elastic, I'll just lump it all together and call scattering. And again, I'm just looking at the basic things that could happen. And you're missing one. What's the other thing that could happen?
It could pass directly through the material, interacting with nothing.
Correct. Nothing. Okay. So when it comes through, depending on what type of material you have, so let's look at some of the variables here. If we look at X, which is the thickness, you would think the thickness might make a difference. If we look at the number density, which is N, and this is the number of atoms per volume of material. Obviously, the more atoms that you have in this material, the more likelihood you have of something happening. And then also, if we turn this sideways, so that instead of the neutron coming in this way, we turn it this way, and now the neutron is striking it this way, this would be the surface area. And that might also have an impact on what type of interaction we have and how many interactions we might have. Okay. So if we look at the chance of an interaction, we could say that this chance of an interaction is a function of the thickness, the number density, the surface area of the material. When you actually go in the lab and you have a neutron, or you have a beam of neutrons, or you have a flux of neutrons, you can measure what these interactions are. And as it turns out, this function turns out to be some constant times the things that we have just talked about, which are the thickness, the number density, and the area. And this constant for the interaction, when you plot it, turns out to be sigma. And sigma is not plane stress. Unfortunately, if you looked at, and I'm sure electrical has the same, as well as mechanical and others, all engineering fields tend to use the same Greek or Roman letters. And so they'll mean different things in different, but this is cross section here. It's plane stress back in materials or civil engineering aspects. So sigma is the probability of a neutron interacting with an atom of the target material. It usually has with it a subscript and the subscript denotes the type of interaction. And basically the ones you'll see will be sigma S, where this stands for scatter. You will see sigma A, this stands for absorption. And again, this is the probability of a neutron traveling through some material. We need to know its thickness, number, density, surface area. There will be a probability of an interaction due to scatter. There's also a probability due to absorption. Those are the main two that you have for interactions. If we add these two together, we have sigma T, where we call this the total probability of an interaction.
Do we have a sigma n for nothing?
No. This tells you the probability of an interaction. If it doesn't interact, then nothing happens. But there is no sigma n for nothing. So this is the total probability. Usually you're not looking at a single neutron. Depending upon the text you use, the context you use, you'll either see this written as I, which stands for intensity, or big phi, which stands for flux. If we look at, I tend to use flux all the time. Your book might interchange the two, but they really mean the same. So if you look at flux, did Professor Abel go into the units for flux? Did he cover flux at all?
I don't believe he did, but I could be wrong.
Anybody? You remember him talking about anything? I'm particularly interested in, if he did, what the units are. And the units turns out to be neutrons per square centimeter per second. And what that means is if we go back to our target, and the flux is coming in this direction, if I take this, rotate it 90 degrees, so this is the face of the target, so the flux is coming in out of the room into it. If I take this and I create a little window that is 1 centimeter by 1 centimeter. So on this side, if I'm sketching it, it's a 1 centimeter by 1 centimeter. When I sketch it, rotate it this way, you can see this little window, and the flux is coming from the room going through it in that direction. So this area is 1 square centimeter. So what the flux tells you is that this is the number of neutrons that is going through a 1 centimeter by 1 centimeter little square of the target each and every second.
Professor, when you wrote the sigma S plus sigma A, what is the sigma S and what is the sigma A? What is underneath that?
scatter. Sigma
the other
S
one
is
is
the
what?
probability of a scattering interaction. Sigma A is the probability of an absorption interaction.
Okay, thank you.
Typically add these two together to come up with a total probability of an interaction. But this is the definition of flux. Flux is a vector quantity, so to be precise, I should put a little hat on it, because it has both a magnitude, which will be the number that you have here, and it has a direction. For example, in this case, it is heading toward the target. All right. If we go back and your book has worked this with intensity, but we could just as easily do it with flux. So I'm going to do what the book has done, but I'm going to use flux instead of intensity. As the flux enters this material, whatever it might be, it has an original value of flux before it hits the material. Then it goes through at any point, it would be the flux evaluated at that point where this is 0 and we're starting x in that direction. So you could go this distance, measure it, go a little dx distance further, and that would be the flux of x plus delta x. If we look at what happens when you go through some little incremental value, delta x, we will have a decrease in the flux. We're going to lose neutrons due to scattering or absorption. And what is this a function of? It's going to be a function of the original flux coming in. It's going to be a function of the number density or the number of atoms we have per volume of material. It's going to be a function of how far you've traveled. And then, of course, we have to consider the probability of having that interaction. For right now, I'm going to keep this probability of interaction being total. Well, remember, the total probability is the probability of scattering plus the probability of absorption. If we look at this, so this is the loss of intensity in flux. As you go some distance, dx into a material, we know it's a function of these three things. If we separate this, if we integrate this over all possible flux values, we integrate this over all possible x values, we're going to have an equation that looks very familiar. We've used this before in natural radioactive decay, other things. The flux at any point x as it goes through a material is the original flux that comes in times e to the minus n sigma t and x. So let me write that again up here. So the flux traveling any distance through a material is equal to the original flux times e to the n sigma t x. So if we have a single material, and we have a number density of material here. If we know what the material is, we can utilize this equation to see what's going on. So let's just randomly pick one from the back of the book. Let me pick
I don't know if you saw it, but somebody asked, is there supposed to be a negative sign before the n in the equation?
yes. Thank you. And we know that because we originally had the negative there when we integrated. Thank you. So let's pick a material like molybdenum. So let's like this material, molybdenum. We have a flux that's going to go through it. Let's make this flux 6 times 10 to the 16th neutrons per square centimeter per second. We'll say that this flux is a thermal flux. And I'm going to go more into thermal, epithermal, and fast fluxes later. Did Professor Abel go into thermal flux at all as to how you define thermal flux? Thermal flux, or any flux, will have associated with it an energy, a temperature, and a velocity. We consider thermal flux to be room temperature, and that temperature is 20 degrees Celsius, which is 293 degrees K. They have measured the velocity of a neutron at room temperature and is 2,200 meters per second. If you put this value back into the energy equation, where Ke is equal to 1/2 mv squared, where this is the mass of a neutron, and we use this velocity, this energy turns out to be 0.0253 eV.
Can you, I can't really see the temperature. That's 20 degrees Celsius.
20 degrees C, and then we add, to make it absolute, we add 273 degrees.
And what is that word on top of on top of the 273?
That, I'm telling you, that's room temperature. And room temperature is considered to be 20 degrees Celsius, 293 degrees Kelvin. Where this is centigrade and this is an absolute value. So this is how you define thermal flux. It's also how you define a single neutron in it, which is a thermal neutron. So if we look at what is happening for our neutron flux that is thermal, we tell you that this is the value of the flux going through molybdenum, we're going to have to find out some values for molybdenum. So if you look at molybdenum in the back of your book, it'll tell you that, what page is that on? That is on page 580. It'll tell you for molybdenum that the atomic mass is 95.911. It'll tell you that the density is 10.22 grams per cubic centimeter. And if you look further across, it'll tell you the cross-section for absorption thermal, and that value is 27, and the units are barns, where 1 barn is equal to 10 to the minus 22nd meters squared. So barn is, even though it's a probability, it's actually an area.
What is the value, not the volume, the unit for E?
Here,
For E.
electron volt.
No.
Electron volt.
For the
This
right
E
side. No, the other one. The lowercase.
over here,
To the right. All the way to the right under A.
here.
Yeah.
This is rho for density.
Oh, that's row. Okay. Yeah, but what is that value over there though? 10.20.
10.22 grams per cubic centimeter.
Okay.
And again, I'm getting these values from the back of the book on page 280. And then it will also show you that the cross-sectional value for scattering or thermal is 7 barns. If you have your book, I would like for you to look at that so that you can verify the numbers that I'm getting and how I'm going to use them. So if I have this flux that's thermal, that's approaching molybdenum, and let's say I make that thickness 5 centimeters, I can ask you for this flux striking molybdenum, what is the flux that the detector measures? We're going to go back. We have developed this equation to determine the flux after it's gone a particular distance x. So if we look at this equation, how many variables do we have? And what are they?
Somebody just asked, is 1 barn equals to 10 to the negative 24 meters squared or centimeters squared?
Centimeters squared.
Okay. And sorry, before you move on, I did have a question I was just scared to ask. How did you
Yep.
find the E, like that value? What did you do again? No, the other
This
one.
one?
No. The capital E.
This one?
Yeah.
This one?
Yeah, how did you find that?
If you know the temperature is room temperature, it has been determined that the velocity of a thermal neutron is 2,200 meters per second. If we go back to the definition of energy, kinetic energy is equal to 1/2 mv squared.
Yeah.
If we throw in the values for a neutron,